Okay, welcome back. In this video, I'm going to do a complete demo of the catalog procedure described in the last video. So if you haven't watched that, it won't make much sense. I'm going to do that with the help of the Enigma machine simulator written by Brian Neal. I will link his GitHub page in the description. It's been fairly heavily modified by me so that it can do some extra things and so that we can run the catalog procedure here in this Python Jupyter notebook. So you'll need to understand a little bit of Python to really appreciate what's going on, but I'll try and explain what's happening as I go through. So I've set up a machine which I can't remember the settings from, and we're going to try and figure out what the configuration of that machine was, what its ground settings were based on some simulated intercepted messages and a simulated catalog. So I've set up some variables already so that we're ready to go. In particular, the catalog is stored in this variable cat. Cat's a Python dictionary. It maps triples of cycle types represented in the obvious way to a piece of configuration data consisting of the rotor order and some information about the wheel settings. So let's see an example of using the catalog. What's in the catalog? We'll look at the most popular cycle type, like this. That's the most popular cycle type. So actually, this is going to correspond to an enormous amount of machine configurations. If you look at how many there are, there's actually 1,728 of them. That is 12 cubed for some reason. I expect that's just a coincidence, but we'll see. Yeah, so if we want to see some of what's actually stored in that dictionary, let's just get a few of them. So let me take this and bung it in here, and let's just look at a few of them. The first four, let's say. So the data that you get when you ask for the settings corresponding to that catalog is this, right? You get there are the first four settings which actually correspond to that cycle type triple. They all have rotor order 1, 2, 3. So you put the first rotor in the slow position, the second rotor in the medium position, third rotor in the fast position, and then the first set of window settings is 0, 0, 24. So we'll be identifying the alphabet A to Z with the numbers 0 to 25. So that 0, 0, 24 corresponds to window setting in of A, Y, and no ring settings. Okay, so what else have we got? We've got the permutations A, D, B, E, and C, F. So we know that we can recover those by intercepting enough ciphertext. So I've just got them directly out of the machine, out of the secret machine. Let's just see what they look like. If you want to see one of these, that's a special kind of permutation object. And if we look at it in its cycle form, right there is the permutation AD in its cycle form. Right, that's what it looks like as a permutation of the lowercase alphabet letters. Right, so the other thing we've got is a long list of the encrypted indicators and the ciphertext, which were these encrypted messages from which the permutations A, D, B, E, C, F could have been recovered. So again, let's just have a look at what their data is. If we just do this, look at the first one, that's going to be a tuple consisting of an encrypted a doubled indicator. So it will be the doubled indicator encrypted with the machine ground settings, and then it'll be a piece of ciphertext that's produced by encrypting the plain text using whatever indicator was doubled and encrypted and put at the start of the message. So here the doubled encrypted indicator was this thing that says SRVAZP, and then that corresponded to some plain text indicator repeated twice, and if you take the machine in its ground setting, set the windows to whatever that plain text indicator was, then when you encrypt whatever the plain text was, you get this this ciphertext beginning YJURG. Okay, so the first step in the catalog is to take the cycle types of the three permutations A, D, B, E, C, F, look them up in the catalog, and see what you get. So let's scroll down a bit. Let me try and line this up. There we go. We're going to look up the cycle types in the catalog. So the cycle types are going to be, well, my permutation class has got a method CT, which gives you the cycle type. And CF, CT, that's the cycle type triples. So let's see what they look like. Okay, there they are. So we've got a 1 squared, 3 squared, 9 squared, 1 to the 4, 3 squared, 8 squared, and a 4 squared, 9 squared. Those are my cycle types. As you can see, I've rigged it a bit so that those cycle types are reasonably uncommon. They don't have any 13s in them, so we're not going to get too many possibilities for the machine configurations that can lead to those cycle types. So if we just do this, have a look what's in there. Right, only 2 configurations can actually give you those cycle types for AD, BE, and CF. And the 2 configurations are having the rotors 1, 3, and 2 in the slow, medium, and fast positions, and in the window 6, 0, 23 as letters, that is G, A, and 23 is X. Right, and then there's another one which looks reasonably similar. Okay, so one of those window settings is nonsense. One of those collections of settings is nonsense. The other consists of the rotors, the correct rotors in the correct order, and the ground window setting minus the ground ring settings. So one of them is correct. It's our task to figure out which. So we've got to make some guesses. We've got to take our dummy Enigma machines and set them up according to those 2 possibilities. So let's call the first one guess 1. We can create an object with Brian's Enigma class, and this is how you use it. You set them up from the key sheet just by saying what the rotors are. I've modified this a little bit. That's it, and we want to set the display. The display should be set to, well, we're doing the first machine, so 6, 0, 23. We've got to use letters in here, so 6 is G, 0 is A, and 23 is X. Okay, so there is our first Enigma machine. Second Enigma machine. Let's just let's see what we can do. This time the rotors are 3, 2, and then 1, and this time we want the machine, the display set up to 19, 18, 10, so 19 is S, T, sorry, 18 is S, and 10 is K, so there we go. Okay, so those are our 2 machines. One of those has the correct rotors in the correct order, and has its display set to the difference between the ground window setting minus the ground ring settings, and the other is no good. The other doesn't work. So we've got to figure out which. So we do that, you'll remember, using a method for recovering the plug board and eliminating machines at the same time. So let's start with guess 1. I've got a method for getting the first 6 permutations out, which is this. So this is just that's just a function on the machine which will give us back a triple consisting of the 3 permutations A, D, B, E, and CF. In real life, you would just work out those permutations, I guess, with a little bit of typing on the machine. Since you have it configured in front of you. So there we go. Now what we'd like to do is to compare the cycle decomposition for the permutations A, D, B, E, CF being produced by the machine we just set up with the cycle decomposition of the true A, D, B, E, CF, the one that we recovered from our encrypted messages. So I'm going to print these side by side with a bit of punctuation. that's got the permutations A, D, B, E, and C, CF in it, the ones that we got from the intercepted messages. And then we also want to print out this thing, and I want this cycles. So cycles is a method that produces a disjoint cycle decomposition, and I'd like a bit of punctuation to make things a bit clearer. How long do I want of those? About 55 of those. Okay, there we go. All right. So yeah, pretty unclear whether this is the correct machine or not. Like in the last video, it kind of leapt out at you because I chose a particularly nice example, and this time we've not got quite such a nice example. So we got some work to do to try and figure out, is there a involution, a stackable permutation with, we know that if there is, it's going to have between 5 and 8 cycles, between 5 and 8 involutions. Is there one of those that's going to conjugate each of the upper rows to the bottom rows? So we're going to have to do some work here because it's not so obvious. So let's do this. So the stacker, what can we say? What can we say that it must have? Right. So looking at the first two permutations there, like the first two above the dotted line there, you can see that there's a one cycle consisting of G in both permutations, and a one cycle with N and M. So there's got to be an N, M in the stacker permutation. We've got this one for free. Okay, looking at the second pair of permutations, again, compare the one cycles. We've got E and E, L and L, N, M, and Q and R. So we know N goes to M. Could be that E goes to L, could be that it doesn't. Don't know this yet, but for sure we've got to have a QR. So there's another one we get for free. There's got to be a QR in here. What else can we get? So a good thing to do is to look for cycles which look pretty similar. So if we're looking at the bottom two permutations, you've got those first cycles, DJNS and DJMS. Okay, well that doesn't tell us anything new because we already know that N must be steckered to M. The second one, that looks a bit funny, so let's leave that for the moment. It doesn't look quite right, but we'll come back to it. The third permutation on the bottom row, the third cycle, this AQX and the AGF, again, they look rather different. But let's look at the final two cycles on the bottom row. So the BT, one starts BTW, YCZ, and the next one starts BKW, YZC. Those things look pretty similar to one another. So I think it's a decent guess here that they are actually lined up in the right way. That T is steckered to K and C is steckered to Z. Because if we did that, then these permutations would align completely. So TK, CZ, if we do that, then they match up all the way along, right? The R and the Q, we know they're steckered already. T and the K matches with the T and the K that we've already done, and we already had an idea that E was probably not steckered. So this is a good start, right? We've got somewhere, but we're now a bit stuck because actually we know there must be more. If this is correct, if guess one is the correct machine, there must be more steckers than this. I believe there was always 5 to 8 at this time. So we've got to try. We've got to try something else. So the rest of the things that we've got, the rest of the cycles that we've got as they are lined up, don't look too similar. But let's start by looking at these final cycles up there in the AD permutations. So the reason I want to look at those is that I know that Q is steckered to R, so that top cycle's got a Q in it and the bottom cycle's got an R in it. So in their correct alignment, that Q and the R must match up. So let's type them out in the order so that they match, in which they must match up, to see if we can guess any more stecker settings. So if the top one goes Q, D, R, V, I, X, T, H, C, like that, and then the bottom one, again starting with the R, it will go R, D, Q, V, I, X, K, U, Z. Okay, so that's those last two cycles in the AD permutations realigned, so shifted round. And now things start to look a lot better because we know that Q must be steckered to R. Okay, that's what it looks like. Now D looks on as if it's not steckered. R to Q, we know that already. V to V, I to I, X to X, T to K. We already knew T to K, but now we've got one more bit of information because now we know H must be steckered to U in order to get this, those last two letters matching up with one another. Okay, good stuff. So that's 5. It could be all of them, but I don't think it is all of them. So let's try something else. So let's look at AD again, and let's look at the other 9 cycles in AD. So we'll look at this guy here and the thing below it. So where have they got to match up? I think there are some letters in there which we know to be steckered. So let's have a look. Yeah, we got a K there, and we know that's steckered to T. So when they line up, they must line up with the K above the T. So let's try that. We'll get rid of this because we already figured it out. So we'll start the top one at K. So it goes K, M, O, L, F, E, J, B, S. And the one below it, if we start at the T, it goes T, N, O. Oops. Bad typing kills me again. T, N, O, L, A, E, J, B, S. You can see this looks great already. We're starting to feel confident, if we weren't already, that guess 1 is actually the correct guess. So, yeah. How does that look then? K goes to T, we know that. M goes to M, we know that already. O goes to O. Okay, O and L are not steckered. Then there's another one, right? F, A must be steckered. Okay. And then that's it. The rest of this stuff is unsteckered. So we've got an FA. All right. So now we've got what? We've got six stecker pairs here. That might well be enough. So let's go through them and check. Let's go through the other permutations and check. Because we now know that those stecker pairs are guaranteed to get the two ADs, to conjugate the two ADs to one another. Let's have a go at the BEs. So in BEs, the 1 cycles are fine. Let's look at these 3 cycles. So A will become F. So we get F, S, and then U goes to H. F, S, H. And that is one of the 3 cycles downstairs. Okay, DMO. What happens there? D goes to D, M goes to N, O goes to O in the stecker. So DMO becomes DNO. Again, that matches up. So we're happy with that one. Let's look at the next 8 cycles. So we got B, J, G, Y, K, H, V, C. What's going to happen there? That's going to become B, J, G, Y, and then K becomes T. So B, J, G, Y, T, U, V, Z. And that is exactly this final 8 cycle on the bottom row. Okay, so that first 8 cycle on the top row must get conjugated to the second one on the bottom row, and finally this last 8 cycle here, so FRPZWTXI, our stecker as we've got it so far will conjugate it to A, Q, P, C, W, K, X, I, and that is exactly the first 8 cycle on the second row. Okay, so I'm now so confident that this is correct. I'm not even going to check the last one. I'm pretty certain that what we've got is correct here. You can check it if you like. Pause the video. So I'm now convinced that this is the stecker permutation, and I'm convinced that guess 1 was the correct guess for the machine. So just for fun, and just to kind of give us a bit more confidence about whether that's right, let's have a look at what happened for the other machine. So we'll just change this so it refers to guess 2. Have a look what's going on there. You can see this one, I mean this one really doesn't look right. Like it's not at all like the nice example we saw in the previous video. It's not even like the medium example that we saw above. It's just a mess. So let's stick with guess 1. I think guess 1 is the correct machine. So what we need to do is configure guess 1 with the plug board connections, the stackable connections that we've just found. So my version has a set plug board method. What I want in there is just to give the pairs. So nm, qr, tk, cz, hu, fa. Okay, there we go. So we've got our machine, which we set up with our with the configuration that we got out of the catalogue. We've now worked out that what the plug board settings have got to be, and we're pretty confident we've got the right machine. So we've now connected the plug board to be what we think it is. Okay, so let's proceed. What we've got to do now is use the ANX method to recover the ring and the window settings. Okay, now we're speaking English today, so it's going to be the THE method. So what I've done is, I don't actually know exactly what the ciphertexts are, but I've rigged them up so that about 50% of them start with the letters THE, just as Rejewski told us that about half of, in fact, he says more than half of the German plain texts that he was working with began with the letters ANX. So for us, I've rigged it so that half of our ciphertexts, about half of our ciphertexts, begin with THE. Okay, so let's write a generator to do this. We're going to write a generator which takes an Enigma machine and a set of ciphertexts and applies the ANX method. So first of all, we're going to write a quick way to test whether a prefix, whether 3 letters encrypted with an Enigma machine actually do form a prefix of one of our texts. So we're going to write a dictionary that maps the initial 3 letters of a ciphertext to an index I, the index of I in the list of the index I of the ciphertext in the list of ciphertexts. So we need for I CT in enumerate ciphertexts. Enumerate just gives you the pairs consisting of the number, the index, and the actual entry in ciphertext. And we're going to count how many attempts it takes us. So we'll have a variable to count how many times we've had to try a window setting. So you will remember that in the ANX method, what we got to do is work through all of the possible window settings in our machine in turn, starting with AAA and AAB and so on, until we get ciphertext output that matches a prefix of one of the ciphertexts. And then, if we're lucky enough, we've actually found the correct window setting to decipher that ciphertext. So what we need to do is try all of the possible window settings in turn. So T in editortools.product, I want the uppercase alphabet, and that's this, and I want 3 of them. So this is going to generate all of the triples of uppercase alphabet letters as the index variable T. What do I want to do in here? I'm going to increase the attempt number. I'm going to set the window. I'm going to get the window setting. So T is a tuple of letters. I've got to turn that into a string of 3 letters to use it in my window setting method, or rather Brian Neal's window setting method. He did write that one. So that will make the window setting into this the window setting that we're currently working on. Then we're going to set to that window setting. We'll set the machine window to that window setting, and then what we need to do is encode THE with the machine in this configuration. So I'll call it encoded prefix. And the way you encrypt text with this machine is used the process text method. Okay, there we go. So what we need to do is compare that output to all of the ciphertext that we've got. So I guess in real life, what you would do is sort the ciphertext into alphabetical order by prefix, and that's probably the quickest way to do this. For us, like I made this helpful dictionary D, so I just got to check if the encoded prefix is in D, and if it is, then we'll yield some stuff. So what we'll need to know is the window setting, what attempt we're on, and the index of the ciphertext, which actually gave us our hit. So that's D, accessed at encoded prefix. Okay, so that's the ANX method as a Python generator. So now we need to feed it our current machine, and we need to feed it our list of ciphertexts. So we don't actually have them, so let's make them. That should be, oops, I always make that typing error. So our we had a list of tuples of indicators and ciphertexts. So this should be IC1 for I in indicators. Indicators and ciphertext like this. That will give us just the ciphertext, and then G will be our generator. So we want to do the ANX method to guess one and these ciphertexts. I told you I did that typo all the time. All right, what have I done? So, well, I've made a stupid typo there. That's better. Okay, excuse me. Right, we're ready to go. Right, we've got a Python generator. We just get the next thing out of it. Let's see what the next thing is. Right, the next thing tells us that when we set the machine, guess one machine, to window settings ADW, which we did on attempt 101. If you can read base 26, you would have known that's 101 already. Then the prefix that we got by encoding THE was a match to the first three letters in ciphertext 17. Okay, so what we should do is we should do guess one. Get our machine, set the display to ADW. Actually, isn't it already in that configuration? I don't know. Then get the ciphertext number 17. Right, and then just decrypt ciphertext number 17. See what happens. If we've got this right, we're going to break a ciphertext already. We will have a whole ciphertext. So like, even if things later on went wrong, if this works, we're going to get a whole ciphertext. If it not, I mean, there's a decent chance it's wrong, but if it's wrong, we'll just go on to the next hit. So let's see what happens. Okay, we got lucky. We got super lucky. So only 100 attempts, which is really not a lot of work, has actually given us what we can see there as English plain text. Right? We've used X for spaces, like what was used on the original Enigma machine. So you can read off there that it says the whole earth is the tomb of famous men. It's the inscription on the War Memorial in Edinburgh, which some of you may have seen. It's Pericles' funeral speech from the Peloponnesian War. Okay, so we got it. We have found a full text using this this window setting. So that is great news. Like we're making a lot of progress. Actually, we've nearly killed it. So we found that we decrypted this text using the window setting A, D, and W. But we can find the indicator for the message which the sender used for that text, because we can get it by decrypting using the earlier window setting that we found. And the difference between the sender's indicator and our indicator ADW is going to be the ring settings. So we're now ready to get the ring settings. So what we'll do is get the encrypted indicator, which was used for ciphertext number 17. So that should be indicators and ciphertext number 17, and the remember that was a list of pairs, and the 0th element, the first thing in the pair, was the indicator. So we'll do that, and let's print it out just to see what it looks like. Okay, it looks like RRR FZB. Okay, garbage. So that's good. It should look like garbage. So now let's put the machine back into the configuration that we got from the catalog. So that's the window being GAX, and we're going to leave the plug board being in its correct setting. So once we've done that, if we put this encrypted indicator we just found, so oops, get rid of the quotes. If we do this, then hopefully, if things have gone correct, if things have gone well, then we should get a doubled indicator. So fingers crossed. Are you ready? Great. Okay, we've got it. Look, KFJ, KFJ. We've found the indicator that was used to encrypt ciphertext 17. It was KFJ. Okay, fantastic. So let's store that. We're going to use it later. So, like I said, the ring settings, like the true ring settings, the ring settings on the key sheet in the ground setting is the difference between the indicator that was used with the correct ground setting, so the sender's indicator, and the indicator that we found from the indicator that we found from the catalog. So what we need to do is subtract the KFJ, this indicator that we've just got, from the one we got out of the catalog, which is the one we got out of the catalog, sorry, the one that we got just now from the ANX method, which is ADW. Okay, so when we do this, we're going to do, like I've written a method to subtract characters and give numbers. And if I do this, it's going to give some numbers, 10, 2, 3. Let me just try and explain where they come from. Let's think what happens. So K minus A, K is the letter 10, A is the letter 0, so K minus A is 10 minus 0, which is 10, and that explains the 10 at the start. And you've got F minus D, well, F is 2 places ahead of D in the alphabet. So when we subtract them, we get a 2, and you do J minus W. Okay, I promise you, work it out, you'll get 13. We have got the ring settings. Okay, we have found our ring settings, and those ring settings are 10, 2, and 13. So now we can also get the ground window settings. We know the ground ring settings. We can get the ground window settings because they're going to be the sum of the ring settings and the window setting that we found. Remember, our setting GAX that came out of the catalog was the difference between the true window settings, the ground window settings, and the ground ring settings. So we can get back the ground window settings just by adding the ring settings to the thing that came out of the catalog, GAX. I've written a method again, or written a function here to add numbers onto letters. So if we do this, we get QCK, just to make it clear what's going on there. Again, what we're taking is we're taking G and we're moving it 10 places forward through the alphabet. Right, G is 6, move it 10 places forward, you've got 16, that's Q. I take A, move it 2 places forward, and you've got C. Take X, move it 13 places forward, wrapping round back to the start, and you end up at K. Right, we now know everything. Okay, we've broken this. We've broken this enigma. We know the window settings, we know the ring settings, we know the plug board, we know the rotor order, we know everything. We're ready to decrypt the text. So let's go. So we're going to scroll down a bit and do our decryption at the bottom here. Let's just add a few more things so I can scroll that up nicely and we can set what we're doing. Okay, so the only thing wrong with the Guess 1 machine so far is it doesn't have the correct ring settings in it. So let's just put those in. They were 2, 10, 13. And let's set the display to, we recovered the key sheet window settings, the ground window settings, it was QCK. Okay, so now our machine is set up exactly the same as it was set up when the person who encrypted the 0th message configured their machine using the key sheet. So let's have a go. When we can decrypt anything now. Let's just decrypt the 0th bit of ciphertext. So first of all, we've got to decrypt the doubled indicator. So, oops, I wanted to say encrypted indicator. This was my list of indicators and ciphertexts. We're going to take number 0, and then we're going to take number 0 from that, which is the indicator. So we should then decode it using our first machine in its current configuration. So if I've done this right, we should get a doubled indicator. What happens? Yeah, there we go. OFE, OFE. So that is the indicator that was used for the encryption of the first ciphertext. So let's put that in the display. OFE. There we go. And let's decode the 0th ciphertext. 0 and number 1, part 1 is the ciphertext. Here we go. There you go. English text. It is perhaps the picture that I can now see clearest of all of all the set scenes of our lawless life.